Hi, my name is Kenneth, and this is a presentation on my research project for the MSc in Data Analytics program. The title of the project is Temperature Estimation in Permanent Magnet Synchronous Motor Components using Machine Learning. A brief background. An electric motor is a device that converts electrical energy into mechanical energy for driving loads. They can be found in almost all areas, especially in industry, where they are responsible for 70% of electricity consumption and 25% of all electricity consumption globally. Problem statement. It is not uncommon for an electric motor to fail during operation due to the presence of rotating and moving parts, often under heavy loads. These failures can have consequences resulting in the huge financial losses and downtime. Motor faults often manifest with abnormally high temperatures, and about half of these faults are either stator or rotor related. Hence, it is necessary to monitor the temperatures of critical components, especially the rotor, the stator yoke, the stator tooth, and the stator winding. The objectives of this project. Following the problem statements presented in the previous slide, the objectives of this project include cleaning and pre-processing data, building several machine learning models to estimate the temperatures of the rotor, the stator yoke, the stator tooth, and stator windings from external temperature variables and electrical characteristics. Also, an objective is to evaluate the models so as to answer the research question, which is, to what extent can the temperatures of the rotor, the stator yoke, the stator tooth, and stator winding of permanent magnet synchronous motors be accurately estimated from external temperature factors and motor electrical characteristics using machine learning. Implementation. The implementation process is shown in the diagram. There are two sets of experiments. The models in experiment 1 are built from the original dataset, while additional features were derived for the dataset used in the second experiment using feature engineering. The process begins with raw data collected as a CSV file from Kaggle and imported into the Jupyter Notebook environment with the Pandas package. Next, the data was pre-processed by checking for missing values, performing exploratory data analysis and data transformation to gain insights into the data and to prepare the data for modeling. In the modeling stage, several regression algorithms were applied. These exist as packages in the scikit-learn library in Python. Linear regression, k-nearest neighbors regression, random forest regression, and decision tree regression algorithms were applied after splitting the data into train and test sets using cross-validation and the k-value of 10 for generalizability. The models were evaluated on the mean absolute error and the process repeated until better results were obtained. In experiment 2, more features were derived using feature engineering and the process repeated. Dataset description. The table displayed describes the dataset after feature engineering. It shows the independent input variables, which include ambient temperature and coolant temperature. The features derived are voltage magnitude, current magnitude, and apparent power. The target variables to be predicted are the rotor, the stator yoke, the stator tooth, and the stator winding temperatures. Results. The tables show the results from experiments 1 and 2. For each table, the mean absolute error of each model for each of the target variables is reported, representing the performance where the lower the value, the better. Initial comparison of corresponding values between experiment 1 and experiment 2 shows no consistent change, as some models, like linear regression, recorded an increase for variable PM, while random forests recorded a decrease for the PM variable. Further visual analysis is provided in the next slide. Among the 4 target variables, the stator yoke consistently shows the least errors across each of the models applied both for experiment 1 and experiment 2, with a mean absolute error of 0.31 for linear regression and 0.41 for random forests, while the PM variable shows the worst performance with a mean absolute error of 0.58 for linear regression in experiment 1 and 0.68 in experiment 2. In conclusion, in line with the proposed research question, Having observed from the results the insignificance of the engineered features on the performance of the models, with the estimations of the stator yoke consistently performing better than the other target variables, irrespective of the applied model or the combination of features, it shows that of the 4 target variables, the temperature of the stator yoke is the most accurately estimated from data containing external temperature variables and electrical characteristics of the motor, while the PM is the least accurately predicted. Code demonstration. This is the Jupyter notebook containing the programming implementation of the project. To begin, all required packages are imported into the Jupyter environment as shown on the screen. This includes the NumPy package, the Pandas package, and other machine learning packages like the linear regression. This cell is executed by pressing Shift and Enter buttons. This cell is executing, it is done executing, and all the packages are now imported into the environment. Next, we import and explore the data set. This is done with the pandas read CSV command, which takes the data set directory as an argument. A brief view of the data set shows the first 5 observations and the variables in the data set. The dataset description. Some of the variables in the dataset are the ambient temperature, which was measured by a thermal sensor located closely to the stator. We also have the coolant temperature, the torque, the motor speed, and the other target variables such as PM, stator yoke, stator tooth, and stator winding, which are to be predicted or estimated. The dataset is mildly anonymized using the formula standardized value equal to original value minus mean over standard deviation. As a result of this standardization, many of the values in the dataset are negative in value. Initial observation of the data is carried out in order to get more insight about the properties of the data. Using the info command on the data set, we can get information about the data set, such as the number of observations, which in this case is 998,070 observations. Also, we can see that all the features are of numeric type, and the data memory consumed by the data set is 99 megabytes. Also, we visualize the data to get a feeling of the spread of the data using box plots as seen in the figure below, which shows that the data set is not widely spread with not many outliers. We check for missing values, which is done with the isNull function, as can be seen on the screen. There are no missing values in any of the features of the data sets. Okay, in continuation, statistical description of the data set is called using the describe function and transposing the results for better viewing. This returns the count, the mean, the standard deviation, the minimum value, the 25th percentile, the 50th percentile, the 75th percentile, and the maximum value of each feature in the data set, as seen on the screen. Due to initial understanding of the data set from the source on Kaggle, a few observations were made leading to some features being taken out. Next, exploratory analysis is performed so as to get preliminary insights about the data. Starting with correlation analysis of the variables, A correlation analysis is carried out on the data set to understand how the variables relate with each other and with the target variables. From the correlation diagram displayed, the correlation matrix, it is seen that the torque has a very high correlation with IQ. As a matter of fact, it has a perfect correlation of 1.0. Also, the stator tooth has a high correlation with the stator winding, and the stator yoke has a high correlation with the stator tooth. The stator correlations can be due to the fact that these are very close in an electric motor, hence there will be a leakage of heat from one to another. Further processing of the data results in the removal of the profile ID and the torque column, since torque is not required, having shown a very high correlation. Also, a histogram of the data set is plotted for each of the variables so as to understand the distribution of the data set, if the distribution is normal, which is desirable or not. From the results, it is seen that the results are not perfectly normal, but they are reasonably normal to proceed with the analysis. Data preprocessing. Here the data is split into training and test sets. As can be seen on the screen, the target variable, the data set is split into the training set and the target variables. Here the target variables are the PM, the stator yoke, stator tooth, and the stator winding, where X here represents the independent variables and N represents the number of target variables, which in this case is 4. Data modeling. The project is designed into 2 experiments. Experiment 1 has to do with modeling with the original features of the data set. In this experiment, we are using four different algorithms: the linear regression, the nearest neighbors regression, the random forest regression, and the decision trees regression. Execution. This linear regression is executed, and as can be seen, the model is currently training. The model is training. It will be trained for each of the target variables. Training is done for PM, training is done for stator tooth, currently done for stator yoke, and now it is done for the stator winding. Having trained the data set is evaluated. Meanwhile, during the training, cross-validation with a k-value of 10 was used so as to improve the generalizability of the data set. What this does is that it splits the data into 10 different folds, and then the data is trained on 9 folds and tested on the 10th fold. It is repeated 9 other times. In each case, a new fold is kept aside for testing, while the remaining 9 are used for training. Also, the mean absolute error is used as the evaluation metric here. This is explained and justified in the report provided. The training here, LRX1 experiment 1 scores, is initialized as a dictionary to hold the scores from training the 4 different models, the model for the 4 different target variables. After training, this is returned, and here the function which is defined to train the machine learning algorithm is called, and the result is passed into the variable LR experiment 1 scores. And now the model is evaluated, is evaluated for the targets. For each of the targets, using this loop function, the mean absolute error, which is the mean of the LR experiment 1 scores, the mean of is returned as the mean absolute error. The I here stands for each of the targets, either PM, stator tooth, stator yoke, or stator winding. This is executed as shown, and from the results it is seen that the mean absolute error for the PM, which is the rotor temperature, is 0.5847. The mean absolute error for the stator tooth target variable is 0.43, and so on for the other target variables. Similar process is applied for the other algorithms. However, these will not be run. These have been trained here due to their long training time. They have been pre-trained, and here they are evaluated to return the evaluation score, which is the mean absolute error for each of the target variables. Explanation of the random forest training function. Here, a dictionary is initialized to hold the scores for each of the target variables, which of course are PM, the stator yoke, the stator winding, and the stator tooth. Here, an object of random forest regressor is initialized with 20 estimators, and this is passed to the cross validation score function in addition to the independent variables and the target variable. Also, the cross validation value of 10, as in the case of the linear regression, is applied, and the mean absolute error is used as the evaluation metric. This also returns the scores from the training and the evaluation. And here the function is called while passing the independent data sets. Here, the model is evaluated to return the scores as seen. These scores all agree with what was put in the report. Now for the k-nearest neighbors, this also takes a long time to run, and so I'll be explaining how it works here. The k-nearest neighbors, this KNN experiment 1 scores is initialized as a dictionary to hold the values of the scores after prediction. And so here an object of the k-nearest neighbors regressor is initialized with a value of k, and a k value of 1 to 20 is tried using this loop function so as to get the k value that results in the best performing model. As with other cases, the cross validation function is called on, and the KNN object is passed as an argument together with the independent features and the target variable. Here the training of the model is complete as seen, and it is evaluated here. The results remain the same. The process is repeated, very similar for the other algorithms. This is so because most of these algorithms have been implemented in an efficient manner in the scikit-learn Python library, and all one has to do is call the appropriate function, as in this case decision tree regressor, and the rest will be taken care of. For the decision tree, same is done, and here are the results, which correspond with the results presented in the report. And after experiment 1, feature engineering was performed to engineer new features before modeling for experiment 2. This is what the dataset looks like for experiment 1. Here a copy of the dataset is made. A copy is made and named derived. It will contain the derived features. The voltage magnitude function is defined to compute the voltage magnitude from the Q dimension of the voltage and the U dimension and the D dimension of the voltage. Also, the current magnitude is computed from the Q dimension of the current and the D dimension of the current. Here these values, using an apply function, they are applied to the derived PMSM datasets, and when run, the head data shows U and I, which are the new data sets, and also S, which is the apparent power. Here the power is defined as the product of the power of the voltage magnitude and the current magnitude. We continue. Here the features are reordered and in preparation for beginning the modeling. Here is experiment 2, which is modeling with derived features. The same process occurs as with experiment 1, with the difference of the input data set, which now contains the derived features. As with experiment 1, the linear regression is very similar, and on running its execution, the training is going on for the PM target variable, which is currently training. This will happen for each of the variables. Yes, and we do same to evaluate and get the scores here as with experiment 1. We do for random forests. The difference between each of these and the previous experiment 1 is just the data set passed in as an argument for the training. Every other thing remains the same until the end. Here the results the same, corresponding with what is presented in the report. Here is nearest neighbors training and evaluation. Decision tree training and evaluation. The final results were then taken to Excel for processing and visual analysis. The Excel is coming up. Okay, so here are the results from all experiments, and here they are plotted in a chart using Excel. Thank you very much. This is the end of the presentation.